discuss about the Hamiltonian formulation of the Klein-Gordon field. As in my previous video, I have discussed about the Lagrangian density and extended the idea of the Lagrangian mechanics into the field theory by you can say formulating the Lagrangian density, then defining some of the basic commutation relationships, and then defining and proving the Klein-Gordon field from the general action principle, and then guessing the Lagrangian for it so that we can get our particular Euler-Lagrange equation. But in this particular video, we are going to discuss about how to formulate the Klein-Gordon field theory in terms of the Hamiltonian, which is another very fundamental thing, because most of the stuff that we will discuss in the advanced quantum field theory, all of that particular stuff basics is this Hamiltonian formulation. So let me start from the basic. From basic I mean let me start it from the classical point of view, and then we will generalize it to the quantum point of view or quantum field theory point of view. So what I'm going to talk about is that, as you all know from the general classical mechanics, that how we define the Hamiltonian. Generally we define the Hamiltonian as some sort of P, which is the generalized momentum, of course, Q dot, which is our generalized coordinate, and here we will do like a minus Lagrangian. So this is very fundamental relationship between the Hamiltonian and the Lagrangian as we define in the classical mechanics. You can see the Goldstein and you will find this. What I am going to discuss about is that how to extend this particular idea to the quantum field theory view, quantum field theory view. How we can extend this? What are the ideas? And of course the idea is the quantization of the fields. How are we gonna do that? Let's see. So this is how we define basically the Hamiltonian for any of their systems, like in the terms of Lagrangian and the generalized momentum. As you all know from the classical mechanics also, that there are some of the basics relationship that we all know as the Poisson bracket. Some important Poisson bracket is, first of all, let me write it, is x dot, which is the suppose that this is our generalized coordinate, and this is dot, which is the time derivative of this generalized coordinate, and this is equals to the Poisson bracket is like this, represented as this, and this is x and the Hamiltonian. So this is how we first of all define the Poisson bracket, that the time derivative of your generalized coordinate is nothing but the Poisson between the x and h. This is the first, and the second one is also fundamental, which is like p dot, and it is equals to the Poisson bracket p and h. And this generalization we have also studied in the quantum mechanics. If you remember, we have a very important relationship known as the commutation relationship, which is between the x and p. If you remember it, it's between the x and p, and that is, I guess, if I remember, it's iota h bar something, iota h bar, yes. So this is the generalization of the Poisson bracket in the quantum mechanics. And now we are going to study that how to generalize this, and this in the quantum field theory point of view. This is very important, and this is what generally we are going to study about, that how to generalize it. So for this, let me quickly review some of the important things which will be helpful for this formulation. And some of the important thing is, first, this particular sign. As you can see here in our previous video, I have discussed about this particular thing. If you don't remember it, this is the generalization of the Lagrangian in the quantum field theory, and this is nothing but the Lagrangian density. If you remember it correctly, this is the Lagrangian density, and this is generalization of the Lagrangian in the quantum field theory. As you can see here, that if we have to formulate the Hamiltonian in terms of quantum field theory, we have to use the same analogy, and we will define here in another quantity known as the Hamiltonian density, which is represented like this, h and some curly h like structure. This is not a perfect diagram, not a perfect word. Let me rewrite it. It is like this. Okay, so this is the Hamiltonian density, and this is defined as pi of x phi dot x minus this. Now let me explain this. Stop a little bit and think here, that what are the similarities between this equation and this equation. Let me name it equation number 1 and let it equation number 2. What are the similarities between this? If you see carefully, here I have defined the pi like thing. This is not pi, but pi like thing in place of our generalized momentum, and we have defined here phi dot x, which looks like a generalized coordinate and its derivative, which is similar to this, the generalized coordinate derivative, time derivative, and minus, this is our general Lagrangian, and this is the Lagrangian density. So yes, so this is, you can say, the Hamiltonian density we define for our Klein coordinate field, and this is very important. So if you do the comparison, you will quickly find out, here I am going to write it, that first of all, this pi-like structure is nothing. It's known as momentum conjugate, or you can say that momentum density. Okay, this is a right term, momentum density. And as you have guessed, this Lagrangian density, this is Lagrangian density as I have discussed before. And the third thing is this phi of x. So what is this? Oh, don't worry, this is like the label we define for the space-time coordinates, and that is the analogy of the generalized coordinate in the classical mechanics. This is just like the coordinate system. This is like a label in the space-time coordinate. Okay, this is the derivative. So now we have this equation, very important equation, and we have used it. You have used this particular equation to derive this equation of the Hamiltonian density. Just like this, let's try to build up the analogy of the Poisson bracket. This, as you can see here, the 1 and 2, we are going to build the analogy of this in the field theory. And as you have guessed right, what we are going to do, so let's see here how to do this in the field theory point of view. Is, let me define now the commutation, or you can say the more appropriately, the Poisson bracket. So the previous Poisson bracket is this x dot, and that is a Poisson bracket between the x and the Hamiltonian. And the second one, as you have guessed, is of course generalized momentum dot, and that is equals to the p and h Poisson bracket. So in the case of the field theory, this is a slight difference, and that difference is, now we define phi dot x, and that is equals to the Poisson bracket of phi and the Hamiltonian. And just like this, second is the general, you can say that the density, momentum density, and this is defined as dot, here I have to write, and this is defined as momentum density comma Hamiltonian, means Poisson bracket. So these are the two relationships in the analogy of the field theory, and we have used this particular analogy to, you can say, write this particular thing, which is not very different. We have just generalized it. We have just moved into the Hamiltonian density form. So remember here, this Hamiltonian is the Hamiltonian density, not the general Hamiltonian. This is Hamiltonian. This is general Hamiltonian. General, as we have seen in the classical mechanics, general Hamiltonian. Okay. So these are the formulations and the basics relationship we have derived now in the Hamiltonian formulation of the Klein-Gordon field. Now one more important thing is how I can write the Hamiltonian density in terms of the Hamiltonian. So it's simple, just like the fact that this Hamiltonian is nothing, is just the integral over all spaces into the Hamiltonian density. This is density, this is general Hamiltonian, and this is the relationship between these two quantities, integral over all the spaces. Now what our task is to find out how to define now this Hamiltonian density. We have defined the Lagrangian density. If you have watched my previous video, I have derived the formula of the Lagrangian density. Now what about this Hamiltonian density? So yes, we are going to deduce that. How? So if you remember from our first equation, what, that the Hamiltonian density is equals to the momentum conjugate multiplied by x, and here is your generalized phi dot x minus Lagrangian density. So what I can do is that I can use the formula of the Lagrangian density I have derived, and also I will put some of the important Poisson bracket relationship, and we will expand this particular expression, and we'll find out the general Hamiltonian. How are we going to do it? So it's quite simple. First of all, you have to remember what was the previous Hamiltonian we have, previous Lagrangian density we have derived. So the Lagrangian density, as of I remember, so let me write the Lagrangian density here in this side. So I can write that Lagrangian density in this particular formula to expand this Hamiltonian density. So Lagrangian density is generally defined as 1 by half 1 by 1 minute. Okay, so it's defined as 1 by half del of mu phi del of with its upper and lower indices, you know, all that stuff. It's from the, you can say, contravariant and covariant tensor, minus m square by 2, and here is phi square. Okay, phi square. This is the Lagrangian density. I'm going to put this in this formula and let's see what will happen. So you have one more thing. Before substituting the Lagrangian density, I have to also find the relationship between this momentum density and this phi dot x. So for this, let me introduce another very important thing. What? So see this carefully. You remember from the classical mechanics that how we define the general momentum, generalized momentum? Yes, we all remember that generalized momentum is nothing. It's just the Lagrangian density divided by dx dot, where x dot is another time derivative of our generalized coordinate. So this is how we defined. Now in the field theory, which is in quantum field theory, if you will see, this changes into this sign, and this is defined as the Lagrangian density derivative divided by del of phi dot x, phi of x. Just like here we have replaced the x dot with the phi dot x in the quantum field theory, and the Lagrangian with the Lagrangian density, and this is how we define it. And this result, this is a very important result which I will try to emphasize, that this result is exactly equals to the phi dot x. Yes, you have heard it right. This exactly equals to the phi dot x. Now I have pointed out the relationship between this particular momentum density and our space-time coordinate label phi. Now what I will do is, we'll try to write the Hamiltonian. Now this Hamiltonian is equals to nothing. Just put the phi dot x as this particular formula. You will get pi a square x. And now I'm gonna put the Lagrangian. So Lagrangian is like 1 by half. Let me write it clearly. So Lagrangian is minus 1 by half del of mu phi del of 1 minute. 1 by half del mu phi, then del mu phi, and then minus, and again this minus will become plus, and you will get plus m square phi square divided by 2. Yes. Now I will try to expand the Hamiltonian, and that is like the pi square x. So if I will expand this Hamiltonian, let me common minus, and if I will expand this Lagrangian density, I will get 1 by half phi dot square, and here I will get minus 1 by half the Nabel operator phi into Nabel operator phi, and again this same term minus m square phi square divided by 2. So if you will ask that what I have done here, so remember, if you have seen one of my previous video, you will remember. Let me clarify it. Yes, this particular formula, this, you have to expand this. This is known as d'Albertian, and a d'Albertian, and that is equals to the time derivative del by del t whole square minus the Nabla operator whole square. And that what I have done here, I've expanded this, and you will get this result. Even if you have doubt, you can watch my previous video. I've explained this, that what exactly is the d'Alembert. It's just like the simple formula to pack all of the particular derivative to make the formula looks like a bit short. So now I can define the Hamiltonian density as, if you remember, this phi dot square is nothing, is just equal to the pi square. So I am going to write it as pi square by 2, and of course you will get minus minus plus 1 by half del of phi into del of phi. This is the Nabla operator, and minus minus plus m squared by 2 phi square. So yeah, this is our formula, very important formula for the Hamiltonian density for the Klein-Gordon field, and we have derived it using the Lagrangian density and some basic relationship between the momentum density and the, you can say, phi dot x. If you will ask me that what I have done here, that okay, these two terms are okay, what happened to these two terms? So see carefully here that I've derived that phi dot x is equals to the phi dot x. It means this phi dot square x is nothing, it's just the pi x square. So this is equivalent of saying, let me write it here, that this is, see carefully, this is nothing, it's just the momentum density whole square divided by 2. And that's what I did here. This is the divided by 2, then you take the LCM and you will get this. So now we have derived the Hamiltonian density. Now what? Now you have to write the Hamiltonian as the integral of d cube x and the Hamiltonian density, which will be equivalent of writing as Hamiltonian as integral of d cube x, and in bracket here write this particular formula, which is momentum density squared by 2 plus 1 by half del of phi and plus m squared by 2 phi square. So yeah, this is what we were trying to derive. This is very important formula and we have derived it. Now I will end video by just making some of the important conclusions and defining some of the another commutation relationship. Now we have derived the commutation relationship between like x and h. Now there's time to define it in the classical point of view. Now some important commutation relationship that you have to study is the Poisson bracket between phi of x and this is like the momentum conjugate. So you can say the Poisson bracket is nothing, is just the three-dimensional form of the delta function. How? So this is up to you. You can prove this. If you want, I will in the next video. This is very important. There are other relationships that I will do in the next video, but this is for the today's video. We have derived a little bit hectic things, like we have defined that what exactly is the meaning of the Hamiltonian conjugate, Hamiltonian density, how we define from the classical point of view to the quantum point of view, and we have derived a little bit very important conclusions. Now in the next video we are going to derive some of the commutation relationship that is really important. But before that, I'm giving you a little bit of advice that you have to study what known as some of the very basic and fundamental properties of the Dirac delta function, because you will see this. And I'm saying you, if you pick any general book on the quantum field theory, you will see this three-dimensional form of the Dirac delta everywhere. I mean, this is very fundamental in physics. You have to use it each and every time in defining the relationship. Even in the green function, this is there, you will define it. So this is very important. So you can learn the basic definitions and some of the important relationship that is used in the quantum field theory from a book called the Noradine-Zetley. This is a book on the quantum mechanics, but you can check out the appendices from this particular book. In this particular, if you check in the last of some of the pages, you will see appendices, and here discuss a lot about the Dirac delta function, and you can watch this. Okay, so this was my video on some of the basic formulation. In the next video we are going to discuss about some very important another commutation and the Poisson bracket relation. So this is for the today's video.